Hello and welcome to this lecture. We've already seen the part linear transformations play in solving equations. We've seen about range, null, rank, nullity, and how null enters the picture very interestingly. Now we're going to move on a little bit and talk about matrix multiplication. You're all familiar with how to multiply matrices. You might have seen a lot of rules. Where does that come from? How does it originate? Turns out it originates from composing two linear transformation. Composing means doing one linear transformation after another, right? So that if you do, you get ideas from you result with matrix multiplication. Let's see that in this lecture. Okay. So what is composition of linear transformation? So let's say you have two linear transformations, T1 R2 to R2 linear transformation, T2 is R2 to R2 another linear transformation. The composition of T1 and T2 we will denote it by this T1 small circle T2. This is read as T1 composed T2 or T1 T2, T1 of T2. You can read it like that if you like, T1 of T2. T1 composed with T2, T1 composed T2, T1, T2. Okay. So this is defined as the transformation from U to what? See, if you were to do T2 alone, it will be T2 of U. Okay. So I have the U, I hit it first with T2 to get T2 of U. And then the T2 of U gets further hit with T1 to get T1 of T2 of U. Right? T2 of U is of course another vector in R2, right? So of course you can do it with T1 again. So this is composition of functions or composition of transformations. Do T2 of U first and then you do T1 of U. Okay, so this is the definition of composition. Okay, so if you want a better picture, here is another picture. You hit U with T2 to get T2 of U, and then you hit T2 of U with T1 to get T1 of T2 of U. Is that okay? I hope this is clear. This is composition. So the first fact, very easy fact to check, is T1 composed T2 is also another linear transformation. T1 is linear, T2 is linear. You can expect it to be linear. You can write a proof. I've written it here. You can go through this proof and be happy that this is true. It just comes from linearity. You do T2 of a linear combination, you're going to get a linear combination of T2 of U1, T2 of U2, and then T1 again hits this, and you get this. Okay, so it eventually becomes a linear transformation. Okay, so if it is a linear transformation, I can have a basis. Can I not? I can have a matrix representing the linear transformation, right? How do you find the matrix representing the linear transformation of T1 composed with T2? That is the next question, right? First thing is, I will have a matrix for T1. T1 is a linear transformation. I know how to find its matrix. I have a matrix for T2. Now, hopefully, the matrix for T1 composed T2 depends on these two matrices, right? Should be related to these two matrices in some form. That is the relationship I'm after. Okay. So what is that relationship? Let's try that. Okay. If you take the canonical basis E1, E2, remember E1, E2 is the canonical basis. And if you do T1 of T2 of E1, right? How do you find matrix of any linear transformation? The same principle applies, right? You have to find T1 composed T2 of E1 and then T1 composed T2 of E2 and make it the first two columns of the matrix. That's what I'm going to do. So how do I find T1 of T2 of E1? I have to first do T2 of E1. What is T2 of E1? It's just B1, B2, B11, B21, sorry, the first column, right? And then T1 of this is what? Just this matrix multiplied by B1 and B2, B21, right? That I know what to do. Just B11 multiplying the first column plus B21 multiplying the second column and adding. So you get this expression. So you get, notice what you get here. A11 B11 plus A12 B21. A21 B11 plus A22 B2. Is that okay? So this is what I get when I do T1 of T2 of E1. I found already what is T1 of T2 of E1. Now what do I do for T1 of T2 of E2? The same thing. Okay, T1 of T2 of E2. T2 of E2 is going to become B12, B22, and then T1 of that is going to be just this matrix multiplied by B12, B22, and you get the same kind of expression. That's it. I found my first column, I found my second column. So the matrix of T1 composed T2 is just this expression. Is that okay? Okay. So this expression looks a bit complicated. I will unwrap this for you a little bit soon enough. It turns out this is actually what we've always been learning from a young age as the multiplication of these two matrices. Why is that? Let's look at it much more closely. Okay, what is this matrix multiplication and how does it come from composition? You have the matrix of T1 and T2 as before. Let's take a U which is xy. Okay, and then ask the question, and we know for sure, right? If U is xy, T1 of T2 of U is the same as, right? This is represented as the matrix of T1 composed T2 times U, isn't it? T1 of T2 U, matrix of T1 composed with T2 U. Okay. What is matrix of T1 compose T2. We already wrote that out, right? A11, B11, this complicated looking expression multiplied by x1. Now T1 of T2 of u, I can also write like this. T1 of m of T2 times u, isn't it? Now what is T1 of m of T2 times u? It's m of T1 times m of T2 times u. Okay. So what you see here is that this m of T1 multiplied by m of T2 times xy has to be the same as this matrix we had for T1 compose T2 times xy. So from here you define that the matrix multiplication of m of T1 and m of T2 is actually this matrix. So this matrix A11, A12, A21, A22, when you multiply with B11, B12, B21, B22, you get this matrix. So the multiplication of matrices is actually corresponds to composition of the corresponding linear transformations. When you compose them, the matrix that you get is the product of the two matrices that you have in the beginning. Okay, so notice there are a lot of intricate things about this multiplication. It looks like a complicated expression. I will unwrap this for you and describe how to think about this. Okay, so here is the matrix multiplication. One easy way to remember the matrix multiplication rule is the following. When I have A11, A12 multiplying this B11, B12 type matrix, what I get here is A11 multiplying the first row of m of T2. Okay, you take A11, multiply the first row, and then A12 and multiply the second row and then add. Okay, that's the way you make the first row of the product. The first row of the product is a linear combination of the two rows of m of T2, okay, the second matrix, the B matrix, right? And the coefficients of the linear combinations are given by the first row. So you take the first row, multiply with the first row here, take each of the coordinates, multiply by each of the rows here and add them up. You get the first row of the product. Same thing you do for the second row. A21 times row 1 of m of T, A22 times row 2 of m of T2, and then add these two guys, you get the second row. So this is the row-wise picture of the product. You can also do column-wise picture, but the columns you have to start from the other side. Okay, so you write the first column of your product as B11 times the first column here plus B21 times the second column here. Okay, B11 times the first column of m of T1 plus B21 times the second column of m of T1. It goes this way, okay, when you do column wise. Likewise, second column is the same thing with B12. B12 times the first column plus B22 times the second column. You can go and check that all these things will correspond to the exact entries that we had here. Okay. Another way to think of it entry wise is the following, right? So you can go back to this picture. If you look at this expression, how do you get this expression here? It's basically A11 B11 plus A12 B21. Okay, so you look at the first row, first column, multiply corresponding elements, add, you get this. How do you get the first row, second column? You look at the first row here, second column here, multiply corresponding elements and add, you get this. So this is element by element. You can also go row by row, in which case you do in this fashion. You can also go column by column, in which case you do this from the right to the left kind of fashion. Okay, so this way you can easily remember how to do the matrix multiplication. Okay, I hope this the mechanics of the matrix multiplication are clear to you. This should be like, very easy practice for you. Anytime two matrices are given, you should be able to just close your eyes and recall the procedure, either the column one, either the row one, or the entry by entry one, and quickly able to compute. Each of these pictures will be useful for you sometimes. Okay. Okay, here's examples. Okay, very interesting looking example here. So I'm going to use my scaling and rotation examples because those are intuitive. You can picture them very easily. So T1 is scaling x by 1 and y by 2. So it's a matrix 1, 0, 0, 2. T2 is rotating by pi by 4 anti-clockwise. So you know that cos theta minus sin theta cos theta type formula. So 1 by root 2 is sin theta and cos theta. So you have this as the matrix corresponding to it. Okay. So let's do a picture. If you do T1 compose T2 of 1, 0. Okay, I'm going to compose. So I have to do T2 first. So I'll rotate first by pi by 4. I get to this blue point. And then what am I doing when I do T1? I'm going to keep x the same and scale y by 2. So I'll go here, right? So this is my T2 and then T1. So it's T1 compose T2 of the canonical basis vector 1, 0, right? So you rotate and then scale y. Okay, so this is T2 composed, T1 composed T2. Okay. So if you do the matrix multiplication, you're going to get 1, 0, 0, 2. You multiply this, you get this. Here's an easy multiplication. No, you take the first row, multiply by this guy, you will get the same thing here. Take the second row, multiply by these two rows. The first one will go away. This gets multiplied by 2. You get it. Okay, easy to do. Now let's try the other way around. Okay, so far I've hid something important from you. Let's do the other way around. Instead of composing T1 with T2, I can also compose T2 with T1, right? Why not? Right? So I'm showing what happens to 1, 0 when T2 gets combined with T1. T2 gets composed with T1. So when T2 gets composed with T1, I will have to do T1 first. What happens when I do T1 to this? I have to scale x-axis as it is and scale y-axis by 2, but then y-axis is 0 here, right? Y coordinate. So if you scale it by 2, you get 0 again. So T1 simply gives you a blue right on top. Okay, this is interesting, isn't it? So if you apply T1 first, notice you get a different result from here. Now what happens when you apply T2? I'm going to rotate this blue point by 45 degrees, pi by 4. So it just comes here. So here is a very, very interesting property of matrix multiplication or composition of linear transformations. They do not commute. What is commuting? Commuting means you can't do them in any order you like. If you do T2 before T1, you get one answer. If you do T1 before T2, you get another answer. Okay, so you have to watch out for this. So what happens here? You can again check it out with multiplication. If you do m of T2 times m of T1, notice this matrix comes first and that matrix comes next. And now you can use the column picture, right? So this first column multiplies this. You get first column here is 1 by root 2, 1 by root 2. Second column multiplies these columns here. And this gets held by 2, get minus 2 by root 2, 2 by root 2. Notice that this matrix and this matrix are not the same. They are different. Only this entry is the same. The other entries, the diagonal entries are the same, but the off diagonal entries sort of get flipped. So they're not the same. Okay. So this tells you matrix multiplication is not commutative. The composition of linear transformations is not commutative. Okay. So it's a nice simple example to see. That's a brief introduction to matrix multiplication. Thank you very much.